Recently, I came across an interesting physics question. A YouTuber who doesn't believe the Earth is round and outer space is real posed the question, if the Earth is a sphere and gravity is real, what keeps air particles near the top of the atmosphere from flying away into outer space? His argument is that since gravity depends on mass, a single particle of air would experience an extremely tiny force that wouldn't be enough to hold it to the Earth. He said it would take an incredibly strong force to hold it to the Earth. He said that if a lonely particle at the top of the atmosphere were to bounce upward, there would be nothing to stop it. Because the atmosphere is so thin up there, it wouldn't hit another particle and would just travel upward forever. I thought it would be interesting to do the math and see what science actually has to say about this. First, it's true that gravity depends on mass. The gravitational force on a tiny particle is tiny in proportion to the particle's mass. However, the amount of force that it takes to change an object's motion also depends on mass in the same proportion. So a tiny force acting on a tiny particle will affect it just as much as a huge force acting on a huge object would. Any object, tiny or huge, that wants to escape from the Earth's gravity needs to move at a speed called the escape velocity of the Earth. Anything moving slower than escape velocity will not be able to escape, and will either fall back to Earth or go into orbit. So the question then becomes, how fast do air particles move, and are they fast enough to escape the Earth's gravity? Well, we have an equation for that. It's called the Maxwell-Boltzmann distribution. The particles that make up a gas are always bouncing around, and their speed changes with each bounce. But the distribution of speeds is given by this equation. It only took a few quick Google searches to track down enough information to solve this equation. The atmosphere doesn't exactly have a top, but for our purposes we can use the top of the thermosphere at 600 kilometers altitude as the top. The International Space Station orbits lower than that, so we're talking about an altitude where the air is 1 trillion times thinner than it is at the Earth's surface. At that altitude, the escape velocity of the Earth is 8,500 meters per second. The atmosphere there consists mainly of unbound oxygen atoms, and during the height of the day, the temperature can reach as high as 2,500 Kelvin, which is about 4,000 degrees Fahrenheit. Going back to our equation and plugging in the mass of an oxygen atom and 2,500 Kelvin temperature, and integrating from escape velocity to infinity, we get the probability of a given particle having escape velocity or greater. This comes out to 5.1 times 10 to the minus 12, or 1 in 200 billion. In other words, for every lonely particle at the top of the atmosphere that achieves escape velocity, 200 billion are moving too slow to escape. And even in this near vacuum at the edge of space, particles tend to run into another particle after traveling only 10 kilometers or so. Therefore, even the ones that achieve escape velocity will likely hit another particle and be slowed down rather than actually escape. Some of them do escape, though. Scientists estimate that every day around 90 metric tons of our atmosphere escapes into space. But that's 90 tons out of 5 quadrillion. At that rate, it would take 150 billion years for the atmosphere to escape completely. Gravity may be a weak force, but it's more than strong enough to hold the atmosphere to the planet for billions of years.